A rational function is a polynomial divided by another polynomial. And we want to look at how these graphs behave. Like polynomials, we'll still look at x and y intercepts and endpoint behavior, but there's another consideration. How does the graph behave as x gets close to undefined values? In a rational function, we are dividing by a variable, and so there will always be breaks in the graph where there are undefined values. So notice here the polynomial divided by another polynomial. A polynomial could just be a constant. A polynomial can just be a linear function, or it can be something to a higher power. But notice that each of these graphs have asymptotes and breaks in them. So this is what we're going to learn how to do, is to analyze what types of asymptotes they're going to have, where they're going to be, and basically kind of what the graph would look like for these different types of rational functions. Something else I want you to notice is that we're no longer going to be just looking at transformations of the basic function 1 over x with some transformations, but we want to specifically look at functions that are written as a single fraction of two polynomials. Now let's dive in deeper to 5 specific examples. So let's look at example 1. Example 1 is a pretty simple basic graph, similar to what we have been doing before. You see that we have a value, we have x minus 3 in the denominator, which shifts this graph over 3. So we have a vertical asymptote at 3. Notice that something I want to tell you about vertical asymptotes is graphs can never cross a vertical axis. Think of it as a big wall, and this is a wave of water, and it splashes up against the wall, and it kind of can go up the wall or it can go down the wall, but it cannot cross the wall. The reason why is that for this value of x, the denominator would equal 0. So y is an undefined value. There is no y that exists at that value of x. Now, what about horizontal asymptotes? We have an horizontal asymptote here at the x-axis. Now, why is this a horizontal asymptote, and what does the horizontal or the non-vertical, and we're going to call them non-vertical asymptotes because not all of the other asymptotes are going to be horizontal. So the non-vertical asymptotes, what do they tell us about the graph? Well, the non-vertical asymptotes, I'm going to kind of scoot this over so we can see this better. The non-vertical asymptotes tell us the long-run behavior of the graph, or the endpoint behavior of the graph. If I were to zoom out on this graph, as we zoom out, we see that in the long run, as x gets really, really big in the positive direction, or as x gets really, really big in the negative direction, in other words, as x goes to infinity in either the positive or the negative direction, y gets close to 0. Let's just look at it as at a reason for that. Let's just put in 2 for our numerator, and let's divide that by the quantity 1 million minus 3. So when we divide 2 by 1 million minus 3, notice we basically have 0 here. And the bigger that we make x, the smaller that this number becomes. So we see that in the long run, this number is getting closer and closer to 0. Let's look at another example. I'm going to zoom back out, or zoom back in so we can see the graph better. Okay, so example 2. Example 2, we have this function looking very similar to what we've had before with our basic function. We have 3x plus 5 over x plus 2. So in analyzing the graph, we're going to first look at our denominator here, our denominator x minus 2. If we make x equal to negative 2, we have an undefined value. That tells us our vertical asymptote. That's the line the graph cannot cross. We also have a horizontal asymptote. You can tell that it's at 3. So what in this equation tells me that this number is going to get close to 3? Well, for one thing, we could just imagine putting a very large number in for x. We can see if we zoom out on the graph. Let me kind of come back to that. If we zoom out on the graph, in the long run, as x gets really, really big in the positive or the negative direction, as x goes to positive infinity or negative infinity, y gets close to 0. we can see by putting in a very large number for x. So let's put in 1,000 for x. So we would have 3,005 divided by 1,002. You can see that that number is very close to 3. Makes sense. I want to look at another way to figure out what that horizontal asymptote is going to be, and that is by dividing. Whenever you want to find out the long-run behavior of the graph or the non-vertical asymptote, you can just divide the numerator by the denominator. So looking at that division problem, if we take 3x plus 5 and divide it by x plus 2, we can see that x goes into 3x 3 times, giving us 3x plus 6. When we subtract, we get a remainder of -1. So we could write this as 3 plus -1 over x plus 2. And this is the way we were writing the function when we did a transformation. So you were looking at it in this form, but you were recognizing, oh, this number tells me, this -2 tells me the vertical asymptote, and then this tells me the horizontal asymptote. The graph is shifting left 2 and up 3, and this -1 flips it upside down. So we're going to be transitioning from this way of writing a rational function to this way of writing a rational function. But you can always divide and go back to this way to analyze the graph. What I want to point out, though, is that the remainder here that we get, if we make x really, really big, y gets closer and closer to 0, just like in our first example graph. But now we have the plus 3. So now we're saying as x gets really, really big, this remainder gets close to 0, but y gets close to 3. So 3 becomes our horizontal asymptote. All right, let's move on to example 3 now. Example 3, things start to get pretty interesting. Example 3 has 2 horizontal asymptotes. So I'm going to throw, and two vertical asymptotes, and those are because there are 2 places where y is undefined. If we factor the denominator of this x plus 3 over x squared plus x minus 2, we see 2 factors, x plus 2 and x minus 1, in the denominator, meaning that -2 and +1 are both going to give us vertical asymptotes. Those are both places where y is undefined. So let's look at some other features of this graph. Something I haven't pointed out yet, and I could go back and look at the previous example, but whatever the zeros of the denominator are will give us our vertical asymptotes. But the zeros of the numerator, in this case the 0 of the numerator would be -3, the number that makes the numerator equal to 0, gives us our x-intercept. So zeros of the numerator are x-intercepts, zeros of the denominator are vertical asymptotes. Now, what about our horizontal asymptote? Well, it turns out that when you have the degree of the denominator larger than the degree of the numerator, there's no way to divide. If I were to write this out as a division problem, I would say, how many times does x squared go into x? Well, it would be 0. You could write it as 0 with a remainder, but the fact is the horizontal asymptote is going to be 0 whenever the denominator has a higher degree. Another reason for that is that a function that is written as x plus 3 over x plus 2 times x minus 1 could be split up into 2 separate fractions, one with the denominator of x plus 1 and one with the denominator of x minus 1, and both of which behave like individual rational functions. So if x gets really, really big, both of these are going to get close to 0, and added together would be close to 0. How to go from this first representation of the rational function to what's split up, and this is what's called resolution into partial fractions, is going to be the topic of our Going Deeper video. It's also going to be a helpful topic for calculus. So if you want to know how to create the partial fraction representation of the original rational function, check the Going Deeper topic for the week. So if I were to analyze this, I would want to know, okay, that there are 3 asymptotes, 2 vertical, 1 horizontal. Now, how do you know where the rest of the graph goes? Well, one thing you can do is you can substitute a number for 0 in for x and find that y is -3/2 and find, so here's my y-intercept. I could find the 0 of the numerator, as we mentioned before, and find the x-intercept. To find the rest of the graph, I would just have to kind of use my common sense. Okay, there's no other place where the graph crosses the x-axis except at the x-intercept, which makes the numerator 0. So and I can't cross either of the vertical asymptotes, so the only thing the graph can do in this middle section is go up and come down, because I know the y-intercept. So this is the only option for it to do, is to go up and go back down. As far as other points, I would just have to check. So maybe substitute 2 in for x in the equation. There's something called the sign test, which I will also include in the Going Deeper video, that kind of gives you, I'll just kind of mention it here, but basically you could say, if I put 2 into all 3 of these factors, 2 plus 3, 2 plus 2, and 2 minus 1 are all positive numbers, so that tells me y is positive. If y is positive, then the graph clearly has to all be above the x-axis, because y is positive, and obviously it can't cross the vertical axis, so that's the only place to draw the graph. Now this might throw you off here, because you're saying, I thought you weren't allowed to touch asymptotes. Well, the graph can't touch a vertical asymptote since it represents an undefined value, but a graph can touch or cross a horizontal or any non-vertical asymptote. And the reason why is because the non-vertical asymptote just describes the long-run behavior of the graph if you zoom out. It does not tell me about that anything is undefined. So I am allowed to cross. As a matter of fact, I want to show you something kind of interesting here. I want to show you, oh, by the way, before I went on, I just wanted to show you that this graph and this graph are exactly the same graph. I don't think you can see them if I have the black one on, so let me take the black one off. This graph and this graph are exactly the same graph as my original black graph here. So I'm going to turn this one off for a minute, turn off these 3 asymptotes. And I just want to show you an example of a graph that has an asymptote. It has a horizontal asymptote at 0. If we were to zoom out on this graph, we can see that in the long run, this graph pretty much just runs along the x-axis. But look at all those little gray dots. All of those places are places where the graph is crossing over the x-axis. In fact, this graph crosses over the x-axis an infinite number of times, but runs along the x-axis, getting closer and closer each time it crosses. So the x-axis is still the asymptote, but the graph just goes on either side of it, getting closer and closer. Let me, if I were to zoom, let's see if I can, yeah, kind of do this a little bit to show you a little bit more what it's doing. It's going up and down and up and down, but as it goes up and down and up and down, it keeps getting closer and closer to the x-axis. Now, unfortunately, I'm going to have to stop and get my grid back the way it was. Let's look at example 4. Example 4 is different than what we've seen before. I want to show you where the asymptotes are. So let's look at the equation first. We have x squared minus 4 over x plus 1. This is the first one we've seen where the numerator has a higher degree than the denominator. In factored form, this would be x minus 2 times x plus 2. You can see the 2 zeros where we have our x-intercepts, the 2 zeros of the numerator, and then the 0 of the denominator, which is x plus 1, where we have the vertical asymptote. But what about the other asymptote? It turns out there is a slanted asymptote. If we were to zoom out on this graph, we would see that in the long run, and I'm going to zoom way out on this, in the long run, except for where this asymptote is in the middle, the graph just looks like this diagonal line. The diagonal line, y equals x minus 1. The graph actually just kind of follows along that line. Let's zoom back out where we can see this better. So how do we find this line? Remember I said to find a non-vertical asymptote, you divide the numerator by the denominator. So let's take a look. When you divide the numerator by the denominator, and you could do this using either synthetic division or long division, although I think long division seems to make more sense for these problems a little bit since we're not trying to find zeros. We're actually dividing by a factor here. Although you could use the factor, you could use the 0, -1 to do this. Anyway, when you divide, x plus 1 goes into x squared plus 0x minus 4, x minus 1 times, if you want to put it that way, with a remainder of -3. So I can write this as x squared minus 4 is equal to x plus 1 times x minus 1 with a remainder. Okay, so x plus 1 times all of this would give me my original function. So what happens then, remember we're wanting to know what happens as x is going to positive or negative infinity. So let's just be an infinity sign. Okay, so what's happening is x is getting infinitely big. Well, as x is getting infinitely big, this number, x in the denominator, is getting really, really big. So -3 divided by a really big number is getting close to 0. So this is approximately 0. So that means the graph gets closer and closer to x minus 1. So our asymptote is actually y equals x minus 1. It's the actual asymptote. So now notice we could also say, well, you might be saying, well, if x is getting really, really big, isn't this getting really, really big? Yes, it is. So we're saying as x goes to positive infinity, y is also going to be going to positive infinity. Y is getting infinitely big too, but specifically, how is it getting infinitely big? It's getting infinitely big by running along this particular line. So let's go back and look. So we can see here is the line y equals x minus 1, and our graph is just running along that line as x gets really, really big. One more comment about analyzing the function is you can always find the y-intercept by putting 0 in for x. So if you put 0 in for x in the numerator, you have -4 and the denominator 1, and so you'll notice -4/1. Here's our y-intercept 0, -4. All right, one more example. This example is the most interesting one of all. You might expect it to look very similar to the previous example because our previous example had a squared function divided by a linear function, a quadratic divided by linear. But when we graph this, we just get a line. So you might be wondering, well, I thought that you couldn't have a value when x equals 3. So let's see what happens when x equals 3. So I'm going to just so look right here. You can see at x equals 3, y is undefined. There's actually a hole in the graph right here. You can't see it until you actually click on it in Desmos, but there is no value there. If you were just kind of like tracing along the graph, all of a sudden you get to this value and it's undefined. Now you can get very, very close to that value, and so, but you can't get equal to that value. So what happens when we try to divide the numerator by the denominator here? So let's take a look. Sorry, I forgot to prepare this one in advance. I'm going to go down and take a look at this. All right. So for example 5, that's example 4 right above there. For example 5, x squared minus 7x plus 12, if you divide by x minus 3, you get x minus 4, which is no remainder. So it turns out when that x squared minus 7x plus 12 over x minus 3 is exactly equal to x minus 4, except we still aren't allowed to have x equal to 3. So we basically have the line y equals x minus 4, but no value at 3. So we can go back in and actually type in y equals x minus 4, and we see it's exactly the same line. This is what's known as a removable discontinuity. We have two different types of discontinuity. A discontinuity is any break in the graph. For rational functions, we have two types of discontinuities. We have what's called a removable discontinuity. In other words, there's just one little hole right here, and theoretically, we could plug in that hole with one point. The graph appears continuous except for that one hole. But if we go back and look at example 4, we see what's known as the infinite discontinuity. In fact, all of our other graphs had an infinite discontinuity because wherever the graph hits that vertical asymptote, the y values are getting infinitely far away from each other. There's no way to just connect the graph together with a single point. So that is known as the place where we have the undefined value creating a vertical asymptote then is called the infinite discontinuity.